All right, this is AP, AB, and BC Calculus. We're doing Unit 8, Section 11, which is volume with the washer method, revolving around either the X or Y axis. So let's jump right on in. So a washer is just a disc with a hole in the middle. It's also called an annulus. So you'll sometimes hear this called an annulus. An annulus is basically a two-dimensional donut, right? So basically what we're looking at here is we have this outer edge, right? And the radius from the center to the outer edge is big R. And we have this inner section that would be the hole that is cut out of the shape, and the radius of the hole or the intersection is lowercase r, which is blue here. The area formula for an annulus is pi quantity big R squared minus little r squared, right? It is worth noting that this is not the quantity r minus r squared. That would be wrong. It's the r's individually squared, and it's easier to see why that's true if we look at where this formula comes from. The area of the big gray circle would be pi big R squared. The area of the chunk we're cutting out would be pi little r squared. So to find the area of the annulus, we would do pi big R squared minus pi little r squared. If you yank out a GCF of pi, right? If you yank out a GCF of pi, you get this formula, right? So with disks, it was really, really important that we find the correct variable expression for the radius r, right, of the disk. With washers, there are two r values. There's the capital R for the outside radius and the lowercase r for the inside radius, or the radius of the hole. It's really important that we get the correct variable expressions for both of those, or else the whole thing kind of falls apart. That's where the hard part of these problems comes. The most common errors in doing washer problems are incorrect expressions for one or both radii, and then misreading the formula. As I just kind of said, I just set this up on the last page. It is pi, and then in parentheses, big R squared minus little r squared, or you can do it as pi big R squared minus pi little r squared. It is important that you notice that r minus r, quantity squared, is not the same as big R squared minus little r squared. Those are different things, so that's really important. So let's walk through an example. On all of these examples, I'm going to put the disclosure that it is fair game as a non-calculator question, but we're going to do it on a calculator. Basically, the reasoning is that most of these problems are about setting it up correctly. If you have to gut it out by hand, you can, but most of the time you won't be asked to. And it's the same skill set we've seen in pretty much this entire unit when we do stuff by hand, right? So let's go ahead and walk through this. So we have the region bound by two curves. So one of them is a parabola, which we can clearly see. So f is 5 minus x squared. That's definitely this top one, right? And g is x plus 3. That's definitely the line that's in the bottom. This shape is rotated about the x-axis. So here's my axis of revolution, right? That's my axis of revolution to create a solid. So let's look at what happens. I'm going to take a random slice somewhere over here. When I rotate this around, I'm going to get this inner circle. That's the hole. And I'm going to get this outer circle. That's the outside. So you see how we get a disk, right? So this disk is going to have a big radius from the axis of rotation up to the top. That's big R. So it seems to me that my big R is the top curve, which would be f of x, minus the axis of rotation, which is 0. So in this situation, my top curve is just f of x. I can call it f of x in my integrand because they called it f of x in the problem. The radius of the hole is going to be from the top of the hole, which is, it seems, the line g, down to the axis of rotation. So lowercase r is going to be g of x minus 0, or just g of x. Once I know that the area of the annulus is pi big R squared, so f of x quantity squared, minus little r squared, right? So I need to integrate from the first washer to the last washer. So that seems to be from when x is -2 to when x is 1. So my volume is going to be pi times the integral from -2 to 1 of f, which is the big R squared, minus g, which is the little r squared, right? Notice that I can call them f and g, right? All right, guess g was green. I can call them f and g because they were called f and g in the problem. If they called them both y in the problem, I would have to actually write the equation, right? I can't rename them as a function if they're not a function. So when I put this in a calculator, the smart way to do it is to just go ahead and put both of these in as a y1 and a y2, right? And that way I can use them as I need to. So x plus 3, right? And then I'll quit out of here. So what I want to do is I want a pi, so second pi, right? Math 9. And then I know that I put them in the order I saw them, so that's going to be y1 squared minus y2 squared. Notice that I'm not squaring the entire subtraction. I'm squaring each one of them individually. So y1 squared minus vars over to y vars function y2 squared, comma, with respect to x from, oh, that's a squared, not a comma, from -2 to 1, right? And I hit enter, and I get that the value is approximately a 96.132 or 3, depending on if I round or truncate. So the AP is going to need to see that you set this up right. They need to see this integrand with the correct bounds, the correct constant, the correct integrand on the inside. So the integral has to have the integrand correct. And then they need to see this answer. If it were non-calculator, you're going to get some pretty ugly fractions, which is one of the reasons we're not going to spend all of our time doing in this non-calculator. If you were going to do it non-calculator, since both of these are binomials, you would have to FOIL each of them out. So just to be clear, if you were going to do this by hand, you would have to FOIL this, right? Minus, and then you'd have to FOIL, I think it was an x plus 3, right? So you'd have to FOIL all of this out, and you'd get an x to the 4th minus 10x squared plus 25 minus x squared minus 6x minus 9, and then you'd have to clean it up. So if you were going to do this by hand, you'd have to do an awful lot of algebra, and you'd get a lot of and then so clean up, then integrate, right? So I'm not going to do that here, but it's possible. It's definitely within your skill set. It's just tedious and not necessary right now. And again, I don't expect you'll be asked to do too many of them by hand on the AP. All right, so you can go ahead and try P1 without me if you want. We have the region in quadrant 1 bound by these two curves. Notice I needed to specify that I meant quadrant 1 because there is another region where they're bound. So starting at 1, right, and ending at what seems to be x is 2, we have these two curves. What we're going to do is we're going to take this and rotate about the x-axis, right? So this is my axis of revolution going this way. So if we take a tiny little snippet in the middle and draw what's happening, oh, that's terribly asymmetric, and draw what's happening when we rotate, that's close enough. We shouldn't ever let me be in charge of drawing things. So basically what's happening here is I have this outer radius, right? The big radius seems to be the top curve, which is definitely the line, right? The top curve is a line. So g of x minus the axis of rotation, which is 0. So my big R is just g of x. And then the inside radius seems to be the bottom of the two curves, which is definitely f of x here, right? It's the curvy one, minus the axis of rotation, so it's f of x. Once I know that, I can do basically all the setup for the problem, right? So the area is pi big R squared, so that's going to be g of x quantity squared minus little r quantity squared, which would be f of x quantity squared. So the volume is going to be pi, and then we're going to integrate from the first disk, which is 0, to the last of the disks or washers. It doesn't really matter. They're the same thing, just one of them has a hole in it, from 0 to 2. So g of x quantity squared minus f of x quantity squared, right, with respect to x. And if I have a calculator, which I'm allowed here, because they were called f and g, that's really all I have to do, and then I can type and get my answer. Again, if these had not been called f and g, if these had both said y equals, you would have to write the entire equation for each one. You'd have to write the 1/2 x cubed and the 2x, because otherwise it's unclear which one you mean. You can't call them both y, you can't call them y1 and y2. When I type this in my calculator, I already put these in, oops, second one's wrong. I already put in 1/2 x cubed as the first one, so that's my y1, and the 2x is my y2. I'm going to quit out of that, and so then I need second pi, right? Math 9, and I know I want y2 minus y1, right? So it's the y2 squared minus the y1 squared. That's the order I want. So vars over to y vars function y2 squared minus, right, vars over to y vars function y1 squared, comma, with respect to x from what seems to be 0 to 2. So 0 to 2. And I hit enter, and I get this is approximately a 19.148 or 9, depending on if you round or truncate. Now, this is one that you could do by hand. I'm not going to go into it that much, but because both of these are monomials, squaring them is pretty easy, right? So, so if you wanted to do this by hand, I'm not going to go into a bunch of work, but if you wanted to do g squared, it would just be 2x squared, which is a 4x squared. So that's pretty friendly. And if you wanted to do f squared, because it's just a 1/2 x cubed squared, it's going to be 1/4 x to the 6th, and that's pretty friendly. So this actually isn't bad. So this is easier by hand, right? I'm not going to go through all the steps to do it, but if you were going to integrate by hand, it's just this thing minus this thing, which compared to some of the stuff that we've seen is pretty nice, right? That's pretty friendly compared to some of what we've seen. So you'd be able to finish that out. I'm not going to do it, but that's the idea. All right, so let's go ahead and do some with respect to y, right? So the region bound by these curves, one of them is a line, one of them is a parabola, is rotated about the y-axis to create a solid. So this is my axis of rotation. So I'm taking this region and I'm rotating this way, which means this is going to have a really big hole and a really thin ring, right? The ring itself is going to be really, really thin, okay? So again, terrible at drawing symmetric things, but we'll survive. So my big radius is from the axis of rotation to the outer curve. So my big radius is going to be the right curve, which is definitely the parabola. So 6 minus 2y squared minus the axis of rotation, which is 0. Now here, see how this isn't called like f of y and g of y? They're both called x. I have to write the entire thing. So I have to write 6 minus 2y squared. I don't have a choice. For the little radius, it's going to be the axis of rotation to the line. So the little radius is going to be the line, which is the 5 minus y, minus the axis of rotation, which is 0. So I just get 5 minus y. So when I go to write this, my area is pi big R squared minus little r squared, right? So that's going to be pi. My big R squared is going to be a 6 minus 2y squared quantity squared minus a 5 minus y quantity squared. It has to look like that. You can't use x and x because they didn't call them f of y and g of y. That means my volume is the integral from the bottom y value. Now this is a little bit tricky. Oh, that's mean of me. Let's erase that for a sec. This is a little bit tricky. This is not a nice happy y value, so you're going to have to find it. This one is definitely a 1. So it's pi, and it's the integral from some number I have to figure out to 1, right? And it looks like it's probably a half, but we're going to verify that it's a half of this thing. 6 minus 2y squared, quantity squared, minus 5 minus y squared dy. So I need to find this, mystery bound, right? I need to see what bound this is. Now, my guess is it's close to a half, but we can't just use an eyeball to guess if it's not a whole number value. So we need to find when these two things run into each other. So let's do that real quick. So let's figure that out. So I need to find when these two things run into each other. So we'll do that. Drag this down to the bottom for a sec, and we'll sort that out. Didn't mean to be mean there. Sometimes I'm just accidentally mean. So, okay, so we need to know when 6 minus 2y squared equals 5 minus y. If I move everybody, I'm going to move everybody to the right-hand side because I'd really like my 2y squared to be positive. So I'm going to get 2y squared minus y minus 1, right? So that seems to be a 2y and a y, and a minus 1 and a plus 1. Yep. That factors correctly, so I get y is negative 1/2. So that is a 1/2. I didn't say negative before, but obviously based on its location. So that is a negative 1/2, but I just needed to check that it was true. So we have to find that negative 1/2. So if it's a non-calculator section, you would then have to FOIL a bunch of stuff out. Oh, you could have also put them in your calculator and found their intersection. I didn't think of that. I just got 2 on autopilot. You could have, you definitely could have done y, oh, my bad. You definitely could have put y1 in as 6 minus 2x squared, and you could have done y2 as your 5 minus x, and then you could have second calc intersect, and you'd get the 1/2. You'd get y as 1/2. Remember, you'd actually get x as 1/2, but you need to know that your x is actually the y value, right? AKA y. So if it's non-calculator, you'd have to do it by hand, but since I'm saying you can do this on a calculator, that would totally be a viable option. So 6 minus 2, remember, I'm putting in x squared, but I know that the x's actually stand for the y's, right? So 5 minus x, right? And then I go ahead and quit out of this, right? And I'm going to go ahead and do, honestly, I could go ahead and hit enter if I want and just plagiarize my own work, right? I could copy my work, so second enter. The trick here is that if we look at which one I called y1 and y2, I called y1 the squared, right? And I called y2 the line, so that looks like I would need to reverse what I have here, right? So I'd need to make this vars over to y vars function 1, and then this one vars over to y vars function 2, right? And then I want to do with respect to x, but it's not 0 to 2, it's negative 1/2 to 1, right? And then I go ahead and, I didn't mean to hit graph, my bad. I hit enter, and there we go. So I get that this is a 36.756 or 7, depending if I round or truncate. Right, so here you had to find a bound, but it wasn't a horrible version of finding the bound, but you did need to find one. All right. Okay, so let's go ahead and do the same concept, right? So this is your P2. You can certainly do this without me if you want. So we have these two curves. We have the y cubed, which is the curvy thing, and we have the 4y, which is the not so curvy thing. It's the line, right? And we're rotating about the axis of revolution that is the y-axis. So what's happening is I take a little slice here. This slice is rotating around this way to create a hole, right? And then this is the outside of the annulus, right? So my outside radius, my big radius, should be the line, right? This is the line minus the axis of rotation. So my big R should be the line, 4y, minus the axis of rotation, so it's just a 4y. My little radius should be the one that is closer to that value, so that's the curve. So that's going to be the curve minus the axis of rotation, so it's just a y cubed, right? It seems like I'm integrating from y is 0 to y is 2, right? That's the top value. So my area is pi big R squared minus little r squared, which is going to be pi 4y quantity squared minus y cubed squared. And this is one that, again, because they're monomials, you could clean this up pretty easily and do by hand. But since we have a calculator, why not? So the volume is going to be pi times the integral from 0 to 2, because that would be the first one of these washers, and the last one is at 2, of 4y quantity squared minus y cubed quantity squared. And you don't have to clean that up on an AP, right? Now, if you're doing it by hand, you would have to clean that up, right? But here you don't have to. So I'm going to go ahead and put in my y to the third, but again, I'm going to put it in as x because we're using x when we integrate on the calculator, and my 4y, but I'm going to put it in as x, right? And I'm going to delete that extra x. So when I quit out of here, I notice that I want the y2 minus y1. So I'm actually going to second enter twice because I already have a y2 minus the y1, like the y2 squared minus the y1 squared. And then I just need to change my bounds. Oh, I don't actually, because they're also 0 to 2. So pi, the thing I called y2 squared minus the thing I called y1 squared with respect to x from 0 to 2, and I hit enter, and there's my answer. So I get 76.595. Again, this is one that by hand would be pretty easy, right? Because this is a 16y squared, and this is a y to the 6th. So this is pretty friendly by hand. So you would be able to do this one by hand without a whole ton of work. It wouldn't be awful, but we're not going to do it here, right? So you could do this one pretty easily by hand. Some of the others, that's not the case. All right, so we're going to go ahead and do some where a calculator's required. So we have this region of an ugly graph that we don't know what it looks like yet, but that's what the calculator's for. We're going to get a look at it. We're going to set up an integral to find the volume of the solid when this area is revolved around the x-axis, and then we're going to find the volume of the solid. So we're definitely leaning on a calculator here. This is not non-calculator at all. So x squared e to the x and negative 2.5 x squared plus 3.4. So check, double, triple check that you entered everything right. And then I'm going to zoom 6. I'm going to assume that that's a decent window normally. Okay, so this is the area I want, right? So if it helps you to draw a really basic graph, you're doing this. It's this thing and then something that kind of looks like this. This is the area that we want, okay? And we're revolving around the x-axis. So here's my x-axis. This is my axis of revolution. This is the area that I'm looking at, right? So what's happening here is I'm going to take a little slice of this and rotate around, right? I did a bad job of drawing it, but you get the idea. Actually, let's fix that for a sec. You should pick a slice so it's not touching the axis of rotation. So there'll be a hole in the middle and then this outside ring, right? So what I notice is that this guy's definitely the frown, right? That's the frown. So that's the thing that I called y2. That's definitely the frown. So the big radius here is going to go from the top of that frown down to the axis of rotation. So it's going to be g of x minus the axis of rotation, or just g of x. Again, because it was called g of x in the problem, I can call it g of x, which makes my life a lot easier. The little radius is going to be from the axis of rotation to that bottom curve. So the little radius is going to be bottom curve, which was f of x, minus the bottom of that line. So this curve minus this line. So I'm going to get f of x, which means that the area of this thing is pi big R squared minus little r squared, or pi g of x quantity squared minus f of x quantity squared, right? And then my job is just to find the two values that I'm going to integrate from, right? So I do need to find these two values. So there's a value right here and there's a value right here, and I need to find them. So I'm going to go ahead and I'm going to call them A and B, right? B I shouldn't because I used A for area, but so I'll just say area just to be clear. So I'm going to call this one A and this one B. So I'm going to find A, I'm going to find B, but honestly I can write my integrand before I do that because I know I'm going to call them A and B. I know that it's pi g of x. Oh, I don't know why I put the pi twice. Come on, brain. My bad. All right, so g of x quantity squared minus f of x quantity squared with respect to x, and then type and get an answer. So I need to find those points of intersection. So second calc intersect, right? I go over here, enter, enter, enter. I get that this is a negative 1.095227, but I'm going to quit out and store that as alpha a, right? Then I'm going to go back to my graph, second calc intersect. Scroll here, enter, 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 right? I see that B is a 0.8401615, right? And I'm going to quit out, X, store as alpha B. And then I go ahead and do pi, math 9, of, I see that it's what I called y2, so vars over to y vars function y2 squared, my bad, minus vars over to y vars function y1 squared, comma, with respect to x from alpha a to alpha b, right? I double check that everything's where I want it, and then I hit enter, and there's my answer. So 42.911, and that's it, right? So cool. All right, so for P3, again, you have two functions, right? We're definitely using a calculator here. Let's go ahead and start by graphing them. So as always, I put them into my y1 and y2 in the order in which I read them, because that way it requires less thought on my part to remember which one's which. So 2.3x squared minus a 5x cosine of x, just a reminder at this moment that you should make sure you're always in radian mode, plus a 3, right? And then my second function is a 1.9x plus 3. Cool. And I can do a quick double check for my mode, but I should be in radian. Okay, so do a quick double, triple check that you entered this correctly, because again, if that goes wrong, then the rest of the problem goes wrong. And I'm going to zoom 6 because usually I can see things in the standard window. So this is the area that I'm talking about, right? So I have a graph that kind of looks like this and like this. So basically, this is the area that we're talking about, right? And then I'm revolving about the x-axis. So if we draw a little slice here and rotate, what's going to happen is that my big radius is from the axis of rotation up to the top curve, which is definitely the line, right? So my big R is the line, g of x, minus the axis of rotation, which in this case is 0, so just g of x, right? My little radius is going to be from the axis of rotation up to the bottom curve, so my little radius is going to be f of x minus 0, or just f of x, right? So my area is pi big R squared minus little r squared. So I can go ahead and write that that's pi g of x quantity squared minus f of x quantity squared, right? My volume is going to be the integral from the thing I'm going to call A to the thing I'm going to call B. Again, you could use two different letters, that's fine. So the volume is going to be the integral from A to B of a pi, and then g of x quantity squared minus f of x quantity squared with respect to x, right? And then I'm going to approximate an answer. I need to find what a and b are, right? So I'm going to go ahead and do second. I could set up the integrand without finding them, but in order to actually finish the problem, I'm going to have to find them, and I wouldn't get credit for the integrand in its entirety without writing the numerical value for a and b. So second calc intersect, enter, enter, enter. That'll give me the first one. Hey, look, it's 0 and 3. That's convenient. So a is just 3. So you could arguably just say, okay, cool, so that's a 3. You might not even bother with the a, right? You might just say, hey, cool, it's a 3. Second calc intersect, scroll to the other one, get as close as I can, hit enter 3 times. Now that one, b, so b is definitely not a nice happy number. So b is approximately 1.334663, dot, dot, dot. So that I'm going to keep as a b. I might as well put the a as a 3. You could also just say, hey, a is 3 and keep it as an a. That's up to you. But again, it is really just the number 3. So I quit out and I hit x, enter, and then I store that as alpha b, right? And then what I'm going to put in my calculator is pi math 9. And then I need the thing I called y2. So I'm going to go to vars over to y vars function, pick y2 squared, minus the thing I called y1, so the same set of steps, except y1 quantity squared, comma, with respect to x from 3 to, that doesn't make sense. It's not a 3, it's a 0. Come on, brain. Hey, people. Sorry, sometimes my brain's slow. The y value is 3, it's a 0. A is 0. Sorry. This was the point, 0, comma 3, and my brain accidentally made the x the 3. Sorry, I take it back. 0, comma alpha b. And those things happen. The reason that my brain had an oh crap, that's not right moment is that I saw that this was a 1.33, and that shouldn't be bigger than the number 3, so I knew something was wrong. Again, you're going to have those moments, so I'm going to leave it in the video because I think it's important to see that we all have those moments when our brain doesn't do the right thing. So there we go. I hit enter, and I get 50.221 or 222, depending on if you round or truncate. So again, that's a 0. A is 0. So just a heads up, and you're going to have those moments where you're like, oops, I did a stupid thing. So there you have it. Okay, so E4 is the same deal. We're talking a calculator required problem. The trick here is that these are curves that are written as x in terms of y, and we're going to rotate around the y-axis. Now, I've taken the liberty of pre-graphing them in my calculator here, so you'll see I put in cosine of pi x plus x squared plus 1, which is this first function, but remember with x instead of y, and then I put x equals y plus 1, but again, the x and y are switched. Now, I did also put the line y equals x, which I put in red here on the slide and here on this slide, and I've made darker on my graph because that line is not one of these two curves. So the reason I did that is I want to show you that if you have a graph that's in terms of x versus a graph that's in terms of y, essentially the function is reflected over this line y equals x. So if you look at my graph, you can see this is the original graph, right? So this is what your calculator's showing, right? And this is definitely the area that we'd be talking about, right? But because this is in terms of x, we have to treat it like we're revolving around the x-axis. But this is what's actually happening. The graph actually looks like a sort of a sideways sort of sigma shape, right? This is the area we're talking about, right? And we're rotating it around the y-axis. You can see that you get the same basic feel by doing it in terms of x, right? But I just wanted to show that this is why the setup is different. So realistically, what's happening, right? So this is my little slice, and here's my annulus shape, right? I can see that the larger radius is going to be right minus left. So the larger radius in this problem is going to be the line, right, which is the y plus 1, so y plus 1, minus the axis of rotation. So my larger r is just y plus 1, right? And I have to write it as y plus 1 because this is not written as f of y and g of y, right? I have to call it that. And my smaller radius, which I guess we'll use, black for because I used a lot of the other colors. My smaller radius here, right, that little r, is going to be the inside curve, which is the actual curvy one. So the cosine of pi y plus y squared plus 1 minus 0. So my little r is just that more complicated function, right? Cool. Once I know that, right, I know that the area is just pi big R squared minus pi little r squared, and then I just, or I can just factor out the pi. The biggest thing is I need to find these 2 points of intersection, right? I need to find here and here. I need to find those that A and B or C and D, whatever you want to call it. So if I want to call this lower value A and this upper value B, right? So the first disk to the last disk, I recognize that the volume is pi times the integral from whatever that A is to whatever that B is, and I don't know them yet, but I'll find them in a second, right? Of my big radius, which is going to be the y plus 1 quantity squared, minus my little radius squared, which is cosine of pi y plus y squared plus 1 quantity squared with respect to y, and then I'm going to make my calculator do the heavy lifting. What I want to show you here is that although this is what's actually happening, and this is what you should be, if you were looking at a picture, this is what's actually happening. What's happening in your calculator is the exact same skill set, right? But everything's written in terms of x. So even though it says rotating around the y-axis, what you're looking at here is you have to treat the x's as the y's, right? So when I second calc intersect, right, when I do my second calc intersect, I'm going to get an a value that is the x value here, and I'm going to get a b value that is the x value here. Again, they're x's, even though in reality in the problem they're y's, because I had to use x as y in my calculator. If you're using something like Desmos, you can actually graph in terms of y in Desmos, and you don't have to do this. Like if you can graph with y as your independent variable in Desmos, you can't do that easily on this calculator, so that's why we're stuck reversing our variables. And again, I just want to make sure that you know how to use it, because in reality, it's unlikely that you'll be using an online grapher in the middle of your AP exam. So I want to make sure you're comfortable with how to do it. So my A is going to be a 0.421588898. And then remember, the step that's important is that I quit out. I take that X value and I store it as alpha A, right? Then I go back to my graph and I second calc intersect, and then I go to the other one. Again, that dark line is not the line we're looking for an intersection. That dark line is just the line we'd be flipping over. So I get 1.354, sorry, 45. Dyscalculia, no joke, man. 458,737, right? And then I'm going to quit out. And again, that important step is that I hit enter and store this as alpha B, right? And then I'm going to go ahead and do what I've done a bunch of times, which is pi. Oops, sorry, my bad. Second pi, math 9. Come on, 9. All right, cool. And then I want the thing, so I called, this was my y1, this was my y2, because I always do them in order. So I'm a y2 first. So I'm going to go ahead and do function to, so that's my y2 squared minus my bears over to function, pick function, pick y1 squared, comma, with respect to x from the thing I called A to the thing I called B, and then I hit enter, right? And I get that this is a 5.789 or 90, depending on if you round or truncate, right? So again, this is really the bulk of what has to happen here. I just want you to get that even though we're doing this in terms of y and we're rotating around the y-axis, you could essentially flip this image and picture it the other way in your calculator. All right, so same concept, right? Different graph. Let's go ahead and do this one, right? So I have a 2.1 x sine of x, right? And then my other one, let's delete these. And my other one is a y plus 2. So I'll use x plus 2 in place of the y, right? Quantity squared. And again, you could keep that y equals x if it helps you to see what's happening, if it helps you to see that you're flipping the graph. It doesn't matter. If it doesn't help, it's up to you. So that's a little bit more complicated. So I'm going to go ahead and zoom 6, right? Okay, so this is definitely the interval that I'm looking at, right? This is the interval I'm looking at here. And again, you could figure out what this would look like flipped. And I'm going to go ahead and show you with the y equals x just one more time so that you can kind of see where this came from. I know it's a little bit of a segue. Okay, so this is what the original graph would look like, right? And I'm just going to show you how I know what the flip graph would look like. And actually, I'm going to do one thing first. It's easier to flip it if you're zoomed square. So I'm going to zoom square, and we can see that this is the interval that we're talking about. There's a bunch of spots all over this graph, but this is the interval where they intersect, right? So if I take this, this is how I was able to flip it, just so that you can see what's happening. If I make a copy of this, basically, if I flip it horizontally, so if I flip it left and right, and then I rotate it until those dark lines line up correctly so that they're at the same spot, you can see what this graph would look like. So that's not quite right. I can rotate it a little farther until they're parallel, but that's close enough. It's not perfect, but it's close enough. All right, so basically, this is the window. We'll just use yellow for this. This is the window we'd be talking about if we were talking about it in X, right? Because again, that dark line is not actually part of the graph. The dark line is just to show you what it would look like if it flips. That's the window we're talking about, right? So what's happening is we're taking this thing and we're revolving around the y-axis, right? But again, you could see it here, right? You could see it here by rotating this way, even though we're not. So this is only in your calculator, right? But this is what's actually happening, right? This is the actual description, but you can use the same logic to figure it out. I just want to point that out, that although you wouldn't write that you were using x's if you were doing this on the AP, the logic would still hold. So what's happening here is my larger radius is from 0 to the outer curve, right? Now it is a little bit hard at first to figure out what the outer curve is, but it's the sine, right? Because if you look, this one, right? This one that's doing, it is the sine, sorry. It's hard to see. So let me erase some of the stuff I put in here. So just to show you the difference, and you could make one of them thicker on your calculator too if you want. The one that's doing this is definitely the sine curve, right? So that's the sine curve. So the outside one is the sine curve. It's a little hard to see when you have all this stuff happening. The one that is just a U shape, right? That's all this is. This is just a U shape. That's definitely the squared term, right? So point being, my outside R is from this axis of rotation to the sine curve, right? The one that has a sine. So the right is going to be the 2.1y sine of y minus 0. So we would just say that it's 2.1y sine of y, right? That's my big R. My little r, right, from here to the inside curve, which I'm drawing poorly, but you can see that that would work. And at some points, the inside curve does touch the x-axis, but that's fine. So the value from here to the inside curve would be this curve, the y plus 2 quantity squared minus 0, which would just be the y plus 2 quantity squared, right? That's my little r. So that means that if I can find these 2 points of intersection, right, and I'm going to erase this again just so we can see what we're talking about. If I can find these 2 points of intersection, right, the lower one to the higher one, those are going to be my a and b. So my volume is going to be pi times the integral from a to b of my big R squared, which is going to be the 2.1 y sine of y quantity squared, minus my little r squared, which is going to be y plus 2 squared squared, or you could write it as y plus 2 to the fourth. Sorry, don't do both. You could write it as y plus 2 squared squared or y plus 2 to the fourth with respect to y. And then I just need to find a and b. So I'm going to do that by doing second calc intersect, right, which is 5. And I'm going to scroll as close as I can to where I think they're hitting each other. Now, I didn't follow my own rule. I found b first because I usually go the farthest to the left. So let me go ahead and do that again. So let's go ahead and redo it. I could have started with that, but I prefer to follow my own rules, which is I always start with the one farthest to the left. So there's my a. So I get that a is approximately negative 2.98594, dot, dot, dot. So I'm going to quit out. That's my x value, right? And again, even though it's an x here, we know it's actually a y in the problem because I switched my variables, right? I go back to my graph, I second calc intersect again, I scroll to the other spot that I already accidentally found, I see that that x is in the right spot. So my b is approximately negative 0.8463345, dot, dot, dot. I quit out of that, that's my x, and I store that as alpha b, right? And then I go through the same thing I've done a bunch of times, right? Now in this case, my y1 is first, right? So I'm going to go ahead and do second pi math 9. I go to vars over to y vars function y1 squared minus vars over to y1 function y2 squared, comma, with respect to x from alpha a to alpha b. And I hit enter, right? And I'm going to get that this is approximately a 57.673 or 4, depending on if you round or truncate. And that's our video.